Okay, one more thing I want to talk about briefly, and you have a homework problem which asks you to study an example in the text, has to do with estimating interaction times. And it turns out that this is just not an easy thing to do, so see section 2.7. But the basic idea is that if we can that some certain processes, we'd like to be able to estimate how big a force is. So if you fall off your bike and hit your head on the curb, we'd like to be able to figure out how big the force on your head is. Hopefully you're wearing a helmet. If you and another student are running to class and not looking where you're going and you collide and stop dead, it would be nice to estimate how big a force you exert on each other. In order to do that, we have to be able to estimate an interaction time. So if we consider a situation where we have two students running to class and they collide and just stop, it's easy to estimate what their initial momentum was. So the mass of an average person might be what in kilograms? Well, what's your mass? So it's about 2.2 pounds per kilogram. So 90 is a big person, sure, 90 kilograms. And about how fast does somebody run? Somebody who's not Usain Bolt. So Usain Bolt can run 100 meters in less than 10 seconds. Significantly less. I don't know what his current time is. Do you know what his best time, recent time is? 9.35. So pretty fast. So that's 10 meters, better than 10 meters a second. So presumably most of us are not going to run that fast. So 6 meters a second. So that would be px initial for this student. If the students collide and stop dead, what's px final? Yeah, so px final is 0. So we could say that px final, px initial plus f net x delta t. If we could so we have 0. We have 6 times 9 is what? 54, so 540 kilogram meters per second. If we knew delta t, we could estimate the force that you exert on each other when you collide. So it's short, right? You stop pretty fast. If we guess a time, if you just guess off the top of your head, what's a short time? Quarter of a second. Quarter. Okay, so let's say it takes a quarter of a second. So now a way to think about this is that during the collision, there's certainly some movement of your centers. So you compress a bit and they get closer together. So if your speed went from 6 meters a second to 0, you have an average speed of 3 meters per second, assuming a constant force. And if you're traveling 3 meters per second, then delta x would be 3 meters per second times 0.25 seconds. So a quarter of 3 meters is a little less than a meter. 3/4, 0.75 meters. So that says that you would travel this far during the collision. Okay, that's probably too far, and that suggests that we are not very good at guessing times. So let's do it backwards. If we say that you traveled about 3 centimeters during the collision, and your guess was actually closer than most people. Most people guess a second is a short time. So 0.03 meters is 3 meters per second times delta t. So 0.03 divided by 3 looks like delta t is going to be a hundredth of a second or less, so very short. Given that, we can actually work out an estimate of that x component of the net force, and I, at this point, suggest that you read this section of the textbook in 2.5. It's really big. So don't do it. Don't run into each other running to class. It's not healthy